Hello, dear students. Today we continue the cycle of lectures on physics, and this lecture is intended for first-year students of the Medical Academy. The topic of today's lecture is the electromagnetic field. Let's remember what an electromagnetic field is. Let's find out how to generate an electromagnetic field. We will also analyze what types of electromagnetic waves emit and also analyze the processes that occur in the tissues of the body under the influence of high-frequency currents and fields. At the last lecture, we analyzed the issues that relate to the action of low-frequency currents and fields, analyzed what effect they have, and how they can be used in medicine. But before we begin to analyze the concept of an electromagnetic field, we also need to remember what an electric and magnetic field is. Here on the slide, we have shown the types of electromagnetic waves, more precisely, the scale of electromagnetic waves. In other words, radio waves, microwaves, infrared thermal radiation, and also ultraviolet X-ray gamma radiation can be distinguished here. That is, a fairly wide range of electromagnetic hills. They all have different characteristics, IDS wavelength, and we look at radio waves. Here, the wavelength will have the maximum value compared to gamma rays. Gamma rays do not have a minimum wavelength of maximum frequency. Accordingly, the actions of all these types of electromagnetic waves will be different on the human body. This application will also be different. In other words, today we will consider in detail the use of high-frequency fields of currents. That is, it is a range of radio waves. In the following lectures, you will also get acquainted with the use of optical radiation, X-ray radiation, and find out how these types of radiation can be used in medicine. Here we also have a range of electromagnetic oscillations shown on this slide. A scale of electromagnetic oscillations is shown. And what else can you see here? The fact that we have some ranges overlap. In other words, there is no strict separation by wavelength and frequency of various radiations. That is, for example, our X-ray radiation is covered with ultraviolet radiation. Here, the division into different types of radiation occurs depending on the method of obtaining. But in the long-wave range, these radiations can overlap, but also in the frequency range. So, well, we are just dealing with these concepts. But we also need to stop as well as how the electromagnetic field and waves act on the human body to recall some factors. Briefly, we will now consider these applications and actions on the body. Well, since the last lecture, we have figured out that electromagnetic fields and waves have an irritating effect, a damaging effect in the range of low frequencies, and also constant currents of fields. In other words, these ranges have an irritating stimulating effect, so we can use them only in a limited way. In addition, it can also be said that we still have low-frequency currents and fields in pulsed mode that can be used for physiotherapy. And in addition, high-frequency currents and fields are already more widely used for physiotherapy. In addition, high-frequency currents and fields can be used in surgery, and also in surgery, we can use laser radiation, gamma radiation, which also refers to electromagnetic waves, to dissect tissues. The next application is the diagnostic use of X-rays. Well, of course, we use X-rays not only in the diagnosis, but also in the treatment of various malignant diseases. And the next thing is the use of light in therapy. Again, we use light not only in therapy, but it can also be used for diagnostics. It is also used in laboratory research. In other words, the list of possibilities for using diagnostic fields and electromagnetic fields in the treatment of surgery can be continued. We have just shown on the next slide that we have not considered the whole list here, not all the possibilities, and you will need to find out exactly where and for what we can use electromagnetic fields and waves. Also, we have this issue again submitted for differentiated credit. In other words, the 16th question we have is the electromagnetic wave, the equation of the electromagnetic wave, the volumetric energy density of vector coding, and in addition, the classification of frequency intervals of electromagnetic waves. In other words, the first part of our lectures will be devoted mainly to this issue, and we will deal with these concepts. Well, initially we will remember what an electric field is. In other words, this concept was studied in our school physics course. We recall that an electric field is a type of matter by means of which a force effect is carried out on the electric charging of a room in a given field. In order to evaluate the effect of the electromagnetic field on charged particles placed in this field, we use such a characteristic as the intensity of the electric field. The electric field strength is calculated as the force acting on a charge, a single exact positive charge placed in a given field. Well, or we will have to divide the symbol by the amount of charge that is placed at a given point by, this is the intensity of the electric field. The force characteristic has a vector direction, that is, we can estimate the direction of this characteristic. And this characteristic is measured in volts per copper. The next characteristic is the potential of the electric field. This is an energy characteristic, and it is calculated as the ratio of energy, which must again be reported to the exact positive charge, a unit charge, in order to move it from infinity to a given point in the field. In other words, we can divide the energy by the amount of charge. The unit of measurement is 1 volt. The electric field we have has lines of force, that is, it can be depicted with the help of lines of force. Here they are shown. In the event that the field is created with the help of a positive charge, a negative charge, we have the lines of force directed from a positive to a negative charge. In this case, we have a field. The lines of force of this field have a beginning and an end, that is, they start from a positive negative. In addition, there are, and we are going to get acquainted with you today, such fields as vortex fields, which force lines of which have no beginning and end, they are closed. And also here you can also see the lines of force of the electric field in the event that the source of this field is a positive charge. We see here that the intensity of the electric field will be directed tangentially in this line of force. The next thing we remember is the magnetic field. In other words, a magnetic field is a kind of matter that is generated by moving electric charges, and Stett pointed out the existence of a magnetic field around a current conductor. By means of a magnetic field, we have an interaction between moving electric charges. The power characteristic in this case is the vector of magnetic induction, which can be calculated as the magnetic moment divided by the strength of the current that flows through the frame with the current. We have shown here a frame with a current on the area of this frame. This characteristic is also vector and measured in Tesla. In other words, we can evaluate it by increasing the magnetic moment, the moment of forces that act on a frame with a current placed in a magnetic field. And this is the current that flows through the frame with the area of this frame. And here it is still possible to dwell on such a question as the magnetic properties of substances, very briefly. That is, the substances we have, depending on their magnetic properties, belong to diamagnets and paramagnets. Diamagnets, they weaken the external magnetic field. Paramagnets enhance the external magnetic field. Well, and then you can separately move the ferromagnets, which greatly enhance the magnetic background. In general, they have magnetic properties inherent in all substances, because our atom consists of a nucleus and electrons moving in a clone field. In other words, an electron is a charge that makes a movement, and whenever we have a movement of electric charges, a magnetic field arises. Well, depending on the direction of the magnetic field inside the substance, we have a weakening of the external magnetic field, or, conversely, an increase. In order to determine the presence of a magnetic field, we can use a magnetic arrow, which will be guided by the magnetic field in its direction. Or we can use a frame made of a conductor of very small dimensions, and it will also show us the presence of a magnetic field. As for the direction of the magnetic field lines of force, the magnetic field lines of force are closed. In other words, in this case, we have neither a beginning nor an end. Well, in this case we have a solenoid shown, the direction of the lines of force is shown, and also a permanent magnet. In other words, in this case we have shown that the direction of the lines of force goes from the North Pole to the South Pole, inside the magnet of the Locke's line of force, and the magnetic field. In this case, we call them a split field, because their fields are those fields in which the lines of force will be closed. In addition, it can also be noted that the Earth is also characterized by a magnetic field, and we will dwell on this later. That is, a giant magnet, and we live in a magnetic field. In this regard, as for repeating some questions from the physics course. The next question is the theory of the electromagnetic field, and this theory was continued by Maxov. According to this theory, we have electric and magnetic fields. If they are variables, they cannot exist separately from each other. That is, we have a changing magnetic field that will generate a changing electric field, and an alternating electric field will again generate an alternating magnetic field. In other words, there is no separate alternating electric and magnetic field. We have a single matter, which is an electromagnetic field. And let's find out on what provisions this theory is based. And the first thing we need to remember is the experiments of Faraday, who found out that if there are changes in the magnetic flux through the area of a certain circuit, then there is an EMF of induction, and an electric current arises. And also Faraday's law, the law of electromagnetic induction, we can write down as the following entry is shown here on the slide. The fact that the rate of change of the magnetic flux will be equal to minus the EMF of induction. The EMF of induction that occurs in this case is the code. The minus sign indicates that the resulting induction current will be directed in such a way that the magnetic flux, the magnetic field that will accompany this induction current, will have the opposite direction. That is, it will tend to compensate for the magnetic field that led to the appearance of this induction experience. This is the minus sign of this law. According to the experiments of the Paradell experiment, we can say that an alternating magnetic field leads to the appearance of an alternating electric field. Well, in addition, you can also see Faraday's experiments here. That is, if we shift the magnet to a closed loop, then an induction current will flow along this circuit, and the magnetic field, which in this case arises due to the induction current, will have the opposite direction compared to the magnetic field that causes the appearance of this induction current. Here we have a portrait of Faraday. You can see the years of his life. That is, his discoveries were made quite a long time ago. And here is another illustration that also shows us this parade. That is, the magnet is shifted, the closed circuit is shifted, and according to the device, we can observe just a change in the magnetic floor. The next one is a vortex magnetic field. Just as an alternating magnetic field leads to the appearance of an alternating electric field, moreover, in this case, we have an alternating electric field that will be curved, that is, all the lines of force were closed. The same alternating electric field leads to the appearance of an alternating magnetic field, due to the fact that our electric field is a source of an alternating magnetic field. The maximum called this alternating electric field a bias current. That is, we have a normal current leads to the appearance of a magnetic field. Here we have an alternating electric field that has led to the appearance of a magnetic field. Therefore, just as in the case of current, we will call the alternating electric field, which leads to the appearance of a magnetic field, a current, but in this case, it is a bias current. The bias current can be calculated according to the following formulas. This is the electrical constant multiplied by the permittivity of the substance, multiplied by the rate of change in the electric field strength, and multiplied by the area. In this case, we mean the area between the capacitor plates, between which there is just no alternating electric floor. In addition, we can also calculate the current density. Also, we already said last time, what is the current density? Then, the current strength divided by the area. Well, then we get the following formula. So the electric constant is multiplied by the electrical permeability of the medium and multiplied by the rate of change of tension. Well, or the derivative of tension over time. Well, here we also have one picture that illustrates the fact that we have an alternating magnetic field leads to the appearance of an alternating electric field, a vortex field. The lines of force will be located perpendicular to the direction of the magnetic field lines of force, and vice versa. We also have an alternating electric field that leads to the appearance of an alternating magnetic field. In this case, too, we have a swirling magnetic field, or the lines of force will also be closed. Now let's write down the main provisions of Max's theory. In other words, it is enough for us to familiarize ourselves with these provisions, although, of course, not all the provisions of Max's theory will be shown here. So, as we have found out, every alternating electric field generates a vortex magnetic field, and in this case, the alternating electric field was noticeably displaced. We have already dealt with this. The second position is the law of electromagnetic induction, that every alternating magnetic field generates a zero electric field. In other words, based on these relations, from the facts that we have considered, we can conclude that there is no single matter where an alternating magnetic field is interconnected. So, what is an electromagnetic field? Let's formulate it. This is a set of variables of electric and magnetic fields interconnected and mutually generating each other. That is, if we have an alternating electric field, forever conducts the appearance of an alternating magnetic field. An alternating magnetic field leads to an alternating electric field, and vice versa. There will also be the concept of electromagnetic oscillations. In other words, electromagnetic oscillations are changes in time of electric and magnetic vectors of tension. If these vibrations propagate in space, then we are already talking about the concept of an electromagnetic wave. An electromagnetic wave is the process of propagation of electromagnetic vibrations in space. And if we have said that mechanical waves can propagate only in many media, then electromagnetic waves propagate in all media, including varnish. In order to get an electromagnetic wave, we need the following source. These are alternating currents, which are sources of an alternating magnetic field. There are also alternating magnetic fields, alternating electric fields, various types of accelerated motion of charged particles, and will also be sources of electromagnetic vibrations. The next question is the generation of electromagnetic waves, electromagnetic oscillations. In order to obtain electromagnetic oscillations, we need to use an oscillatory circuit. The first figure shows a closed oscillatory circuit, which consists of an inductor and a capacitor. If in this case we observe the formation, that is, there are magnetic oscillations in such a circuit, then they will be associated with this circuit and will not propagate in space. We also need to have such an oscillatory circuit, which would have the propagation of vibrations in space. Therefore, in order to achieve the propagation of vibrations in space so that they can be used, we need to separate the capacitor plates when the vibrations are already propagating in space and reduce the number of turns of the coil. That is, as a result, we get this kind of oscillatory circuit in which, in principle, we have an inductor already represented by a straight wire, and at different ends of this wire, we have a capacitor plate. Usually, after all, the capacitor plates also decrease in size, and we get small capacitors in the plate area. Well, or in general, they are connected to the wire. In other words, we will already have such an oscillatory circuit as a source of vibrations that will propagate in space. Well, in this case, it can also be noted once again that in the capacitor we have the formation of electrical oscillations that change in direction and magnitude. Inductors occur periodically change the magnetic field, also in size and direction. Now let's see what an open oscillatory circuit looks like, what can be obtained as a result. That is, we will have an open oscillatory circuit consisting of an alternating voltage generator. Here we have an alternating voltage generator here, and we have conductors connected. Alternating current will naturally flow through the conductors. We have it shown here, just here with the arrows. The white and blue arrows show the direction of the current. That is, according to the period, we have a current flowing in one direction. According to the period, we have a current flowing in the other direction. Around these conductors, since we have AC conductors, an alternating magnetic field arises. The alternating magnetic field, we know from the theory of the maximum, leads to the appearance of an alternating electric field. An alternating electric field arises. Again, an alternating electric field leads to the appearance of an alternating magnetic field. Alternating magnetic leads to the appearance of an alternating electric field, and so on along the chain. We have the propagation of electromagnetic vibrations in space. An electromagnetic wave propagates. Thus, an open oscillatory circuit, which is equipped with an alternating voltage source, we will call a radiating antenna or an oscillator. In other words, this oscillatory circuit is the source of an electromagnetic wave that propagates in space. Well, it can also be noted, with regard to the mechanism of occurrence of an electromagnetic wave, that an alternating electric current creates a vortex alternating magnetic field. A vortex alternating magnetic field leads to the appearance of a vortex alternating electric field, and so on along the chain. In other words, in this way we can create an electromagnetic wave that will propagate in space, and we will use it later. This figure also shows the mechanism of generating electromagnetic waves. That is, there is again an alternating voltage source. There are two conductors. The direction of the current changes after half a period. A magnetic field arises around the conductor, and an alternating electric field will propagate around this magnetic field. In other words, an electromagnetic wave will propagate in space. Here we show the propagation of the magnetic component of the electromagnetic wave. Just as for a mechanical wave, we wrote down an equation. For an electromagnetic wave, we also write down an equation, but in this case, the equation will consist of two components. These are the electrical component and the magnetic component. In other words, in this case, we see that the electric field strength will vary according to the harmonic law, and also the magnetic field strength. H is the strength of the magnetic field. The second force characteristic of the magnetic field also changes according to the harmonic law. Well, the magnetic field strength is measured in amperes of elements, which allows us to evaluate the force effect of the magnetic field on the moving charged particles of the vacuum. Also in this formula, we see that there is purity, a circular frequency, and in this case, we also get a dependence on time, denoted by the letter T, dependence on the coordinate or on the distance from the source of this wave x, and also depending on the speed of propagation of the electromagnetic wave. In this case, E and H are the instantaneous values of the electric and magnetic fields. E0, H0 is the amplitude value, that is, the maximum value of the intensity of the electric magnetic background. Omega is the circular frequency. X is the distance from the emitter to the velocity spread over the magnetic path. And U are the time. That is, once again we stop there. According to these formulas, according to this equation, we can also draw a graph of an electromagnetic wave. Well, either we have to fix the time or fix the distance. In this case, we have a graph showing a fixed point in time, depending on the distance. And in this case, we see that we have a vector of electric field and magnetic field intensity that will oscillate in mutually perpendicular planes. That is, the vector E we have oscillates the vertical plane vector as much as the horizontal plane. In addition, they also oscillate perpendicular to the direction of propagation of the electromagnetic wave. In other words, based on the fact that our oscillations occur in the planes of perpendicular poisonings of the propagation of an electromagnetic wave, we can say that an electromagnetic wave is transverse waves. In other words, light, as one of the types of electromagnetic wave, will be a transverse wave for us. In other words, let's recall that a mechanical wave in the form of sound, in the form of ultrasound, is a longitudinal wave. Here we also note that light, X-rays, radio waves are transverse waves. Here we have another graph shown. We also have an alternating voltage source, an electromagnetic wave source, and we see that in this case we have oscillations occurring in mutually perpendicular planes and a perpendicular direction of propagation. Well, you can also look at the dynamics of how we have changes in these vectors and how the electromagnetic wave propagates in space. The next question that is important when considering any physical factor is the energy characteristics of an electromagnetic wave. That is, depending on the energy, we will have an effect on the body to varying degrees. In other words, the more energy, the greater the impact the physical factor will have on the human body. The electromagnetic wave, its energy, it will consist of two components. This is the electrical component depending on the electric field strength, and the magnetic component depending on the magnetic field strength. We can estimate the energy using the volumetric energy density. That is, here we have this formula. This formula includes, again, the electrical permeability of the medium, the electric constant, the electric field strength squared. In addition, we can also note that there will be a magnetic permeability of the substance, a magnetic constant, and, well, the intensity of the magnetic floor. In other words, the energy that will have an impact on the human body, on biological objects, will depend on these terms. In addition, we also need to evaluate the effect of the energy impact with the help of the vector of the mines of the coating. The vector of smart potting is calculated according to the following formula. So, the density of the energy flow, that is, the energy that propagates up to a unit of time and through a unit of area, will be determined as the electric field strength multiplied by the magnetic field strength. In this case, we are talking about a vector product, that is, the vector product of the electric magnetic field strength, and in this case, this ratio will also be equal to the volumetric energy density multiplied by the speed of propagation of an electromagnetic wave. Based on this formula, we can conclude that our propagation velocity will determine the direction of the Coking vector. In other words, we will have the Coking vector directed in the same way as the speed of propagation of an electromagnetic wave. The next question is the significance of the electromagnetic fields of its biological objects for biology, for medicine. We have already noted that the Earth is a giant magnet, so we have a magnetic field of the Earth. And besides, we must also take into account that all biological processes originated on Earth. In the conditions of the existence of an electromagnetic field, the electromagnetic field of the Earth, as well as other objects, stars, and other planets. Therefore, there is a natural electromagnetic background, and now we have both pollution of the electromagnetic background with the help of artificial sources of electromagnetic background, and also there are such phenomena as, on the contrary, shielding from the electromagnetic background. The natural electromagnetic background, if a person is, for example, in conditions of a long stay in an airplane, in a rocket, in a car, and in this case, the electromagnetic background, of course, it will already decrease. Naturally, all of this can also have an impact on the human body. And as for the effect of electromagnetic waves of a technogenic nature, it is also necessary to take into account that the applied effect of fields of sufficiently high intensity can cause a violation of health. So, well, here you can also see that the sun is the senior source of the electromagnetic field, which will also affect a person. And as for the significance as well, as I would say, electromagnetic wave fields can have a negative impact with prolonged exposure, and also if the intensity of this factor is high. In other words, there is such a thing as an electromagnetic valent when there is a violation of the central nervous system, reproductive system, cardiovascular system, but this is as it were, provided that it is a sufficiently high intensity of prolonged exposure. And besides, we can also use the electromagnetic field, electromagnetic waves for therapy, that is, in certain dosages, with certain indications. We can use these factors for treatment. But again, in each case there are contraindications, so they also need to be taken into account. The next question is the scale of electromagnetic waves. We have already looked at it at the beginning of the lectures. It is possible to divide it depending on the method of obtaining. And here we have what types shown: low-frequency vibrations, radio waves. We also have optical radiation. This includes infrared visible radiation, ultraviolet radiation. Also, X-ray and gamma values can be attributed here. Let's find out in which case we get one or another type of electromagnetic waves. So, radio waves can be obtained if there are alternating currents in the conductors and also in the presence of electronic flows. The sources of the radio wave we have is the antenna learner. In the case of optical radiation, that is, we refer to infrared, ultraviolet visible radiation as optical radiation. These types of radiation will be obtained due to quantum transitions of electrons in external orbits. This is about the optical presentation. Well, if we look again at the visible region of the spectrum, then here again we do not have a clear division. In this case, we have one transition range and another. This is a feature of electromagnetic waves that we also have. The next type of radiation is X-ray radiation. X-ray radiation is obtained by breaking fast electrons on a solid target. This is the first method of obtaining, and also for quantum transitions, on layers close to the core. We will have a separate lecture dedicated to X-ray examination, and there we will analyze the ways of obtaining action on the body. Applications in medicine. The next radiation guide is gamma radiation. We can get it from the decay of radioactive poisons. Gamma radiation is characterized by a maximum frequency, respectively. It will have a maximum energy effect. Well, in this case, navigation will have a strong enough impact on the body, a negative impact. In other words, this also needs to be taken into account. As for X-ray radiation, which borders on ultraviolet radiation, here again we do not have a clear division by wavelength. Then X-ray radiation can also be used in medicine, since it is characterized by ionizing effects. Therefore, it can be used only in a limited way. Here we also show the scale of electromagnetic waves in comparison with the size of the wavelength and some objects. That is, if we consider the radio range, then the wavelength here is quite large. That is, we measure the size of buildings. If microwaves, then there is already the size of a butterfly and so on. In other words, if we look at the violet radiation, the dimensions will be comparable to the sizes of molecules. The wavelength will have such a value. X-rays already have a wavelength that we compared with the size of atoms. But the gamma radiation here, in this case, the wavelength dimensions will correspond to the size of the nucleus. That is, from a wavelength that is comparable to the size of the building, to one wavelength that corresponds to the size of the core. And such long waves characterize electromagnetic radiation. This is about the first part. Now we turn to the second part of the lecture. And the second part of the lectures we have relates to high-frequency currents and fields, their effect on the body, and also their use in medicine. We can say that we refer to high-frequency currents and fields as total fields, the purity of which lies in the range from 100 kHz to 10 to the 11th power. Up to 100 kHz, we consider low-frequency oscillations. Also, depending on the purity of the high-frequency topics, electromagnetic fields can be divided into three categories. It is of high frequency from 100 kHz to 30 MHz, from 30 MHz to 300 MHz, and over high frequency, it is over 300 MHz. The effect will naturally differ in this case, and the application here, if we talk about physiotherapy, then depending on which tissues we affect, it will be determined by the frequency of this physical factor. Again, we can recall that the issues that we are going to consider now, they take out for differentiated credit. This is the 17th question of shortcomings. And that's exactly what concerns the processes that occur in the tissues of the body due to the actions of high-frequency fields of currents, as for heat losses or reaction losses. And also with regard to the use of high-frequency currents and fields, we have quite a lot of techniques here. We will not consider all of them, but consider some part. The first thing we need to find out about the effect of high-frequency currents and fields on the body is why high-frequency currents and fields are widely used in therapy, as opposed to low-frequency ones. And here, we will consider the rationale for therapy with high-frequency fields and currents. We have already touched on this issue in the last lecture, and we found out that high-frequency currents are characterized by a sufficiently high frequency, so the current strength here changes quite quickly. Here, we show comparative graphs for the current of the lower frequency of the blue line for the higher frequency. Of course, if we consider low frequency, only high frequency, then there will be a more serious difference. Well, as it was possible to show here, we see that in the case of a low-frequency current, we have a slow change in the current strength, and the current that has an irritating effect will have an effect for a longer period of time. In the case of a high-frequency current, the effect will be observed for a short period of time, so the nerve endings do not have time to react to the action of these currents. Therefore, we will not observe irritation, damage to tissue excitation with the help of high-frequency currents. That is, in this case, there is no such negative impact as in the case of low-frequency current. Therefore, we can use high-frequency fields and currents for treatment. The second thing we can use these currents for is the presence of a thermal effect. In this case, the heating of the tissue occurs due to precisely those processes that will be observed by the actions of only the Fepali. That is, it is not only in conductivity, only in displacement. The movement of dipole molecules and, unlike traditional heating methods, here the heat will be released precisely in the depth of the tissue, and the amount of heat that will be observed, which will be released, will depend on the parameters of the electric field, that is, the intensity, purity, and also on the characteristics of the tissues themselves. Therefore, when we remove the technique, we must also take into account any tissues that need to be affected. Therefore, because in different tissues we have a similar length of heat, depending on the physical factor that we use. And the next effect, which is also used in therapy, is a specific effect. The maximum manifestation of it will be observed with fluctuations of ultra-high frequency and ultra-high frequency. Then there are physicochemical changes, zero molecular changes, structures 4 changes that can also have a positive effect on the tissues of the body. And here, as for this fact, we also apply it in medicine. The next issue is heat loss. Heat losses allow us to estimate the amount of heat that is released in the tissues of the body under the influence of this physical factor. A formula is used here, that is, it is a general formula that allows you to estimate heat losses. That is, the heat losses are equal in terms of the energy that is released divided by the volume by which this energy is released, and by the time during which the release occurs. The unit of measurement in this case will be 1 Joule divided by 1 second and by a cubic meter. Depending on which tissues we have heat release with the help of an electric field, an electric current, we use some other form to assess heat losses. So, if we are talking about heat losses, in the case of a conduction current, that is, if we have electrodes placed directly on the surface of biological tissue, then the delta heat losses are defined as the current density squared multiplied by the resistivity, or the current density squared divided by the electrical conductivity. And of course, with regard to conduction currents, heat losses will occur in those tissues that are rich in liquids. That is, we have already said, that is, where we have ions that lead to the appearance only in conductivity. If we place a biological tissue in an electric field and we do not have a contact overlay of electrodes, then in this case, the heat loss will be determined as the electric field strength squared multiplied by the specific electrical conductivity. In other words, we see that we have heat losses, that is, the amount of heat that will be released in the tissues of the body will depend on the parameters of the electrical factor of tension, current density, and will also depend on what characteristics the given tissue has. That is, it is the specific electrical conductivity, the specific electrical resistance. In other words, they will also determine the amount of heat that will be released in these tissues. This is what concerns the heat losses that occur in conductive tissues. Also, we have a large amount of heat that will be released in non-conductive fabrics. And in this case, we say that there are electrical losses. In dielectrics, we know that we have no free charges, but in this case, we have dipole molecules, and since in the field of a variable, the dipoles will be oriented in the direction of the field, that is, they will tend to turn in the direction of the field. The field is variable, so the field, as we see in the picture here, will make rotational movements. That is, according to the period, they will tend to be located in one direction, according to the period in the other direction. So, dielectric losses are a part of the energy of the electric field, which is converted into heat when repolarized into dielectrics. In other words, we have the energy of the electric field transmitted by dipole. Dipole is moving. In this case, the energy of motion will be converted into thermal energy, into internal energy. In this case, our heat losses can be calculated using the following formula. This is the dielectric constant of a substance multiplied by the electric constant multiplied by the frequency of the electric field multiplied by the electric field strength squared, and the tangent of electrical losses. That is, the delta is the angle between. Here we have shown in the figure between the direction of the electric field strength and the dipole moment. In other words, the dipole moment is a characteristic of the dipole, which is directed from a negative charge to a positive one. That's just the angle between these vectors, determines the angle of electrical losses. The more rebellious, the greater the electrical losses will be. Also, our dielectric losses will be determined again by the characteristics of this substance. This dielectric constant of a substance will be determined by the frequency of the electric field. In other words, the higher the frequency, the more energy will be released in a given tissue. It will be determined by the intensity of the electric field, but also by the angle of dielectric losses. This is exactly what concerns the properties of these tissues. Based on this formula, we can pretend that we can regulate the amount of heat that is released, that is, regulate the purity and tension of the synthetic floor. In other words, we have variable high-frequency fields and currents that have a thermal effect, and we can use physical therapy for thermal effects. The next question is the classification of high-frequency equipment. In this case, let's consider some techniques that are used in medicine for both treatment and surgery. The first method is personalization, a fairly old method that we will offer at Sanvalum. The active factor that affects the tissues of the body is a high-frequency alternating pulse current. Well, the frequency in this case is from 50 to 110 kHz. The voltage is high enough, it's 25 kHz. The current strength is 0 as much as 0.02 of a milliampere. The current has a bell-shaped shape, and the purity of the modulation in this case corresponds to 50 Hz. What impact will this variable impulse current have in this case? I must say that here we are considering local bitonics, when there is an impact at the local level on a certain area of skin, tissue, or on the mucous membrane, and there is also a general technique when a person is placed in a large solenoid and affects it. The general methodology is not actually used now, therefore we are considering the local impact. That is, in this case, the therapeutic factor is an electric discharge that occurs between the electrode and the patient's body. When removing the electrode from the patient's skin, it is also possible to influence without a gap, that is, with a tight contact of the electrode and the human body. We have the electrodes here. They are shown on slides. These are glass electrodes of various shapes. And the electrodes have the peculiarity that the pressure inside is low enough for an electric discharge of pressure to occur inside the electrodes from 1/10 to 5/10 of a millimeter of the foot column. The electrode is attached to our resonator. Here we have it depicted here. We also have this device in our laboratory practice. And then there is an impact. That is, the effect is different, that is, both on the mucous membrane and on the skin. The scalp can be affected by OPA on the gums. Now let's look at the drawings, which just explain the data. And in this case, there is an irritating effect on the skin receptors. In addition, there is also an improvement in blood circulation, which has a positive effect on the tissues of the body. Well, Just here we have drawings that explain the use of personalization. That is, it is possible to affect the scalp with an electrode in the form of a calculation. Also, a mushroom-shaped electrode is used to affect the tissues of the body when the skin is touched. And also the gums, the electrodes we show here. That is, this is already a dental practice. The next technique is the ray therapy apparatus. Here it is possible to use either an ultra-high frequency electric field or an ultra-high frequency magnetic field. The purity of the active factor is from 40 to 50 MHz if we use it in continuous mode. And in a continuous mode, we observe exactly the thermal effect. If we use a pulse mode, then in this case we use a purity of 300 MHz, and here we can observe the specific effect of ultra-high frequency vibrations. What is marked here, that the wavelength here is quite high, at a peak of up to 7.5 meters. That is, there is an impact on not a local one, but an impact on, as it were, all tissues. Well, naturally we bring the electrodes to a certain area. Here the impact occurs as much as possible. If we use an electric field, then capacitor plates are used as electrodes, which are placed in plastic. If we use a magnetic field, then in this case we use a coil placed again in a plastic box, and this coil is already placed on the tissues of the body, on the human body. And just here too, you can see what the elbow joint is affected by the shoulder joint. In this case, we have a non-contact effect. That is, there is an air gap between the human body and the electrons. In this case, the thermal effect occurs both on the conductive tissue and on the non-conductive tissue divides such. Just the maximum amount of heat will be released by the dielectric. Heating in this case will be through in general. Well, we have already looked at this formula for heat losses. In conductors, it will be determined how the electric field strength is multiplied by the specific conductivity and depends on the characteristics of the tissues themselves and the characteristics of the field. As for dielectrics, we have already analyzed this formula with you. That is, the dielectric constant of a substance is also determined. Again, these are the characteristics of the organism, also determined by the characteristics of the field. In other words, it is purity, tension, we can regulate the heat losses, the amount of heat that will be released here, regulate the frequency and intensity of the physical factor. And besides, we remember what is happening here, specific effects with the help of this device at high frequencies, and apply this technique in order to affect the central nervous system, the endocrine and circulatory system. The next technique is diathermy. In this case, there is a through warming. Initially, diathermy changed precisely as a physiotherapeutic factor. Now, it is used only in surgery mainly. And in this case, the therapeutic factor is the conduction currents. The frequency from 50s to 2 MHz affects the surface tissues, that is, the skin subcutaneous fat. If the density is only high enough, then a sufficiently strong heating occurs under the electrode. Moreover, if we have an electrode of a very small cross-sectional area, that is, the tissue heats up to 60–80 degrees, the contents of the tissue boil and thus the tissue is dissected. Heat losses in this case will be determined. We have looked at this formula, how to divide the current density into squares by the specific conductivity. Well, in this case, we have the energy of ions that will move through the actions of this high-frequency current will be converted into internal energy, into thermal energy. In this way, tissue dissection will occur if we are talking about techniques such as electrocoagulation and electrotomin. Electrocoagulation is used to stop bleeding, to stipulate vessels. And in this case, it is important that we have an active electrode with a small cross-sectional area. A passive one has a fairly high cross-sectional area. Since the active electrode has a small cross-sectional area, the current density here will be quite high. That is, if we remember that the current density is the force divided by the area, and the area has a small value, then the current density will be quite large. Therefore, under the active electrode, we have heating to a temperature of 60–80 degrees Celsius. And so, if this is an electrotomy, then in this case, we have an electrode in the form of a small ball, and the passive electrode is flat, the area of which is quite high. If this is an electrotomy, a tissue dissection, then we have an electrode in the form of a blade. Well, here we also show just electrosurgery. I will raise the active electrode. We have a high current density. What we see here is just a passive electrode with a fairly large area. Under it, of course, there will already be so much less dissection occurs only under the active electrode. The device is presented here too. Again, you can look actively, or someone has a small flow area and a passive large enough area, and systemically the current density under the active electrode will be high enough. The next technique is inductothermy. In this case, the active factor is a high-frequency magnetic field. The frequency is from 10 to 15 megahertz. We know that a magnetic field, an alternating magnetic field, leads to the appearance of evolutionary currents, Foucault currents in this case. And due to this, we will have an oscillatory motion of charged particles. The energy of the motion of these particles will be converted into thermal energy, due to which heating also occurs under the influence of induction currents. In other words, we act with a high-frequency magnetic field. We have a magnetic field shown here in the figure. The magnetic field leads to the appearance of eddy currents. In this case, our ions will make oscillatory movements. Since our field purity will be large enough, then it will not have time for us to pass a circular current. Therefore, the irritating, exciting action is naturally not observed here. The energy of the movement of the tachyon will be transformed into internal energy, into thermal energy, and with this, there will be a warming of the body tissues. Heat losses, the energy that in this case will be the energy that in this case will be released, we define as the Meadow frequency of the magnetic field squared, multiplied by the magnetic induction of this field squared, and multiplied by the specific electrical conductivity. Again, we see that in this case, we have a dependence both on the properties of this field and on the properties of the fabric, which in this case expose their revenge. The next technique is microwave therapy. Microwave therapy. Here, the impact we have, in contrast to the action of the will be local. The wavelength of this factor will vary from 1 millimeter to 1 meter. The frequency of the active factor is 10^8 to 10 to the 11th degree. The action will again be thermal. A horn antenna is used as an electron, but the heat loss will depend on both the electrical and magnetic component. The heat losses will be equal, as the shape is determined as the dielectric constant of a substance multiplied by the magnetic permeability of a substance. The magnetic value is multiplied by the magnetic field strength, the electric field strength, and divided by 2. As for this physical factor has the maximum effect on those tissues that contain the aqueous phase. Since in this case we have the purity of this factor, it corresponds to the characteristic frequency of vibrations of water molecules. Therefore, in the water phase, we have the maximum heat released, and the effect of this therapeutic factor is shown on these tissues, where we have an aqueous phase. Here, we have a photo illustrating this therapy with this effect. And the last technique is microwave resonance therapy, F therapy. Here we have an operating factor is an electromagnetic wave of a sufficiently high frequency from 10 to the 11th to 10 to the 10th power of hertz. The wavelength is 1 millimeter. The amount of heat that affects the tissues of the body is determined by the quantum of energy, that is, it is Planck's constant, multiplied by the frequency of the electromagnetic wave. And it was noticed that the maximum effect is provided by the action of this factor on biologically active points. In other words, maximum absorption occurs here, and if we have biologically active points interconnected with certain tissues and organs, then the effect just happens on these organs. The phenomenon of resonant frequencies is also used here, that is, it is at certain frequencies that the body's response to this effect is expected. The impact will be local, and the impact will be a small signal. In other words, these are the features of magnetic resonance therapy, or another name for extremely high-frequency therapy. This concludes our consideration of issues related to the classification of high-frequency therapies. In other words, we have not considered all the methods. There are quite a lot of them. Well, as it were, here are the main types of impact we have considered. And besides, we recall that today we also considered issues related to the generation of electromagnetic waves. The concept of an electromagnetic wave, the scale of the phase of magnetic waves was examined. And as for the following lectures, you will also consider how electromagnetic waves are used in medicine, how this type of electromagnetic wave can be obtained, and what effect they have on body tissues. That's it. We are finishing the lecture. Goodbye.